Okay. So in this example, we have iodopropane and ammonia, and we want to write the mechanism for this reaction, predict the products, and see how solvent will affect the energy diagram of this. And so here again, if this is a substitution reaction, our products are going to be an amine and hydrogen iodide. So that's our products for this, because it's a substitution of a nucleophile with a weaker nucleophile. So I is referred to as the leaving group because it's going to leave, and NH3 is the nucleophile in this reaction. So now we have to decide, is this going to undergo SN1 or SN2 reactions? So again, SN1, the rate determining step is a unimolecular step, and we form a reaction intermediate called a carbocation, and in the second step we have the nucleophilic attack of the carbocation. So there's two steps in an SN1 mechanism. In SN2, it's a concerted reaction where everything happens in one step, and the mechanism is or the rate determining step is a bimolecular step. And so with SN2 though, it does what's referred to as a backside attack of the alkyl halides. So the leaving group leads from the front, and then the nucleophile attacks from the back, and that's where we get the substitution. So we need to identify whether this is going to be SN1 or SN2 mechanism. And so we need to determine the number of carbon groups, or carbon sticks as I like to say, attached to the carbon that's directly attached to the halide. And so here we see that there is one carbon stick group off of the carbon that's directly attached to the halide. So this is what we refer to as a primary alkyl halide. And so primary alkyl halides like or prefer SN2 reactions. So since it's a primary alkyl halide, it's being used in this reaction, it'll prefer to undergo SN2 mechanism because it's not as bulky. It's easy for the nucleophile to attack from the backside. And so for our mechanism, it would look like this. It's a one-step mechanism. Where we get these substituted product. And so here the rate law for this bimolecular step is this. Rate equals K, and I'll draw that in just a second, times NH3. And so this is the mechanism for this reaction, and this is the rate law. Again, it's a bimolecular step, so both reactants are included in the rate law. Also note that there is no reaction intermediate in this mechanism. So now, what would the energy diagram look like? Again, energy diagram, we have energy and reaction progress. So now since it's one step, it's only going to have one activation energy. And again, with substitution reactions, since we're replacing a relatively non-polar bond with a more polar bond, these are going to be exothermic, generally exothermic reactions. So we have our reactants, our activation energy, and then we make products. So again, there's only one activation energy because there's only one step in this mechanism. So here we do our reactants. Those are our reactants and our products. Now at the transition state, if we were to draw what's occurring, we'll draw it over here. So what's occurring at the transition state? So the carbon iodine bond is becoming weakened or getting longer, and the nitrogen is starting to form a bond with the carbon. And while that's going on, one of the hydrogens is about to be increasing its bond length so that it's about to be removed. So that's what's occurring at the transition state. The iodine is slightly negative. The carbon is slightly positive. The nitrogen is slightly negative. And so you start to see this nitrogen-carbon bond start to form, and the carbon-iodine bond start to elongate and eventually break. And that's what's occurring at the transition state. Now, if we were to, let's say this first reaction, or this first curve is in a non-polar solvent. Say we use the solvent, and we'll do it over here. For the green line, for the green curve in the energy diagram, let's say it's with the solvent hexane, which is a non-polar solvent. Now let's say that we change up the solvent, and instead of using a non-polar solvent, now we're going to draw a blue curve where we use a polar solvent. So when I draw the blue curve, we're going to use the solvents. For example, we'll use acetone, which is polar. And so when I draw the curve for acetone, the difference you're going to see is that the activation energy is going to be decreased. And the reason is because the nucleophile, it still be the same, let me erase that, is that the nucleophile, it has better solubility in the polar solvent. So you're going to see a decrease in the activation energy. Now this is not drawn to scale, this is just showing you that when you add a polar solvent, the activation energy is going to decrease because now the nucleophile has better solubility in a polar solvent versus a non-polar solvent. Now let's say we try another polar solvent. We'll make this one a red curve. So here we have a red curve, and instead of acetone, let's say that we're going to use an alcohol like methanol. Methanol is also a polar solvent. Now, when I draw this energy diagram with methanol, we notice it's still lower than the nonpolar solvent hexane, but it's higher when we use methanol versus when we use acetone. And the reason is if I draw you the structure of acetone, and I draw you the structure of methanol, the difference is that acetone is what we refer to as a aprotic polar solvent, meaning it can't hydrogen bond with itself, whereas methanol is what we refer to as a protic polar solvent, which means it can hydrogen bond with itself. And so the reason that acetone provides a lower activation energy than methanol is because if we look at the transition state, you see that the nucleophile is partially negative. And what will happen is if we use a protic polar solvent, the nucleophile may interact with the protic polar solvent through an ion dipole interaction and kind of inhibit the nucleophile from attacking the alkyl halide. So that's why it prefers using an aprotic polar solvent, so there's no interaction between the solvent and the nucleophile. So if you had to do an SN2 reaction, it would be preferred to use an aprotic polar solvent like acetone, DMF, DMSO, and THF. So in our second example, we have triethyl bromide and ethylamine, and we want to determine whether this is going to undergo an SN1 or SN2 mechanism. So again, the products from this reaction are going to be substitution of the nucleophile with the amine. So we want to know, is the mechanism for this reaction going to be SN1 or SN2? Now, if we look at the alkyl halide, we look at the carbon groups or carbon sticks attached to the alkyl halide, we see that we have 1, 2, 3. So this is a tertiary alkyl halide. And tertiary alkyl halides are very bulky halides. They have a lot of what we call steric hindrance. So the fact that there's a lot of steric hindrance means it's going to be very hard for the nucleophile, and again, the nucleophiles are amine. It's going to be very hard for the nucleophile to perform a backside attack when you have all these bulky groups, aka steric hindrance, around that carbon. So when you have a tertiary alkyl halide, it's going to prefer to undergo SN1 mechanism. So that means that we're going to have two-step mechanism, and the rate determining step is the first step, which is a unimolecular step. So we have step 1. I apologize if my lines are not straight. So in step 1, it's just the leaving group leaves the alkyl halide. So we form what's called a carbocation. Here's our carbocation, and we form bromide. That's step one. And now if we write the rate for this step, it's just the alkyl halide is involved in the rate. And again, the first step is always the slow step. So anytime you have an SN1 reaction, the slow step is always the first step. Now, once we have the carbocation, step two, the carbocation gets attacked by the nucleophile. And we get our substituted product. Oops. And H+. So this is step two. The nucleophile attacks the carbocation. Now if we draw the reaction, or excuse me, the energy diagram for this, so again, we start with our reactants. The first step is the rate determining step. It's going to have the highest activation energy. Then we form our reaction intermediate. We have step number two, and then we form our products. Again, this is going to be a exothermic process. So we have our reactants. I'm just going to write them in their formula form, it'll be easier. So we have our reactants. In the first step, we form our carbocation. Oops, I wrote that wrong. So 1 second. That's actually what the formula is. I made a mistake. Again, in the first energy minimum between the two activation energies, we form our carbocation. And then the carbocation gets attacked by the nucleophile, and then we form our products. So again, we have two activation energies because we have two steps. The first one gets the highest energy because it's our slow step. The first step is always going to be the slow step for an SN1 reaction. And so let's say that this curve represents a nonpolar solvent. say hexane. Now, instead of hexane, let's say we use, let me change the color. We use a red for another solvent. Let's say here we're going to use ethanol. Which is a polar solvent. Now, if I draw the energy diagram using ethanol, it would be lower in energy than hexane, because again, the nucleophile tend to have better solubility in polar solvents. Now, let's say we use another polar solvent. Here, for example, we'll do green, and we'll use THF. THF is a polar solvent. So now if we draw the curve, and we see that THF would have a higher activation energy than, say, using ethanol, for example, but it would still be lower than hexane. And so if I draw the structures of ethanol, and THF, let me draw it better. You see that ethanol is a protic polar solvent, and THF is an aprotic polar solvent. So with SN1 reactions, they prefer protic polar solvents, because what happens is that the carbocation gets stabilized by ion dipole interactions with the solvent. And so that stabilizes the carbocation, and therefore giving it more stability so the nucleophile can attack. And that's why protic polar solvents are preferred by SN1 reactions, because they stabilize excuse me, the carbocation.